So good afternoon, everyone. My name is Aydin. I'm an engineering manager at Meta, and today I'm joined by my co-presenter, Maharshi.
Hey guys, my name is Maharshi. I'm an engineer in Meta.
So Maharshi and I have been working on Lineage infrastructure and graph observability solutions for Meta over the last few years, I guess, right? So it has been so long time, right? So, today we want to walk you through the privacy purpose interactive lineage graphs, how we build it, how we achieve it. So probably most of you guys remember the banana data problem from the morning presentation, right? So that's a good analogy, and it only emphasized the billions of flow side, the scale side of the problem. But upon this, we also need to build a graph that is refreshed daily, so queryable in real time and also trustworthy enough to answer most of the privacy decisions and questions. So I want to start one of my favorite questions here, where does data actually flow? So I really like this question. It's a very simple question in plain English text, and also it has been my day job, also my team's day job for the last few years, and I'm glad it exists. So actually, this is not a question that we are asking once in a quarter during a compliance audit. So this is a question is being asked all the day by our engineers who are kind of debugging a violation in their code base, or by our compliance team when they are kind of making an investigation regarding a privacy request, and recently and most increasingly by AI agents reasoning about purpose limitation and similar privacy challenges in real time. So the bar is not in actually answering the question, it's also about how we answer this question. So we need to make it in an interactive way, in real time and across a graph, which is actually both messy and constantly changing. So I want to start with a couple of challenges that we observed on the building or generating the graph side. So actually, when you try to build this graph, especially at Meta, you need to deal with multiple lineage providers. Actually, we have more than 15 of them. They are all great providers. They are purposefully built for solving some problems in some specific set of data systems, and they work really well. They introduce their own data formats, their own freshness guarantees, and they also have their own confidence models. But when it comes to bringing all this together and building an homogeneous system, we also noticed that they are actually not speaking the same language. The first challenge started from this point. And then when we started to bring them together, we also noticed that stitching them is not also easy, because granularity is a big problem. So mostly, we start with focusing on a coarse granularity in a naive solution, right? So we follow the asset granularity approach, but we failed very quickly, because this quickly introduced a lot of false positives into our systems, and we start losing the trust with our customers. Then it comes to the accuracy problem. So when you start introducing low confidence flows, actually you are kind of stealing someone else's time by having them investigating a data flow that actually doesn't exist in reality. So this is also a valid point for AI agents. They can confidently make some wrong decisions if we keep having low confidence flows. So I want to hand off to Maharshi for showing a couple of architectural decisions and technical design issues about this problem.
Thank you very much, Aygun. Yeah, so let's talk about each of those areas which Aygun mentioned. Let's first start with the scaling, right? So let's look into how we actually fit the billions of edges into the graph, which can be solved with a single machine. Fundamentally, the way we try to think about this is when you think about the nodes and edges, and if you just try to store this into plain string approach, then it can take a lot of the size, and you may not be able to fit this into the memory within the single machine. So we try to utilize some of the known compression techniques. So first one is more like integer compression. This is nothing but how you can encode your node and the edge data, and you represent that into the 64-bit of the integer ID instead of storing that as a string. Then the second kind of the approach is a string interning. So instead of you store the repetitive characters and the words into the string, you break it down and you only store something which can uniquely identify this node, so that way you can reduce the size of the data which you want to store. Very similar approach for the tier metadata. So some of the, instead of like storing metadata repeatedly, we try to identify which are the hot fields and the hot metadata, and we try to store that and map that with the nodes which we have defined earlier. So that way we can easily get the data quickly. The other one is the H deduplication. So as Aygun was mentioning, we have around 14 to 15 different lineage providers. One of the core challenges like this lineage providers can have the similar ages they repeatedly send to us. So we try to deduplicate it, and we try to store that uniquely. And the last but not the least is the selective materialization. So at a time, we only load the data into the memory, which is more like relevant to that use case, and then related to the state. So that way we can try to feed the graph into the memory as much as possible. Then let's talk about the granularity and stretching, right? So I think we talk about like how we can feed, how we can compress the graph into the memory. But then there is a next challenge, which is kind of, I feel it is even the real bigger challenge than the previous one we have seen. How we can stitch the data across the different layers, right? So if you take like just a simple example, right, of the application, there can be a web layer where the users are having the interactions, and then we have the service calls from there. And then it might be going into the data warehouse where we are having the different ETL pipelines, which is transforming a data, and it may have completely different format. And then the third layer could be just an AI, ML world model training inference where we may have the data stored in completely different format. So one of the challenges is like how we can stitch this together so that we can get the data end-to-end correctly. We divide this into the layer approach. So first layer is we define the canonical access identity, asset identity, how we can make sure that every node is uniquely identified, no matter from which layer it is coming or which tier of the architecture it is coming. The second kind of the layer is we normalize the edge so that data looks the same, whether it comes from the service log or ETL or AI ML world. And the third one is the explicit rule around like how we can stitch the data from one system to another one, and then that can help us to normalize the data even further. This approach helps us to understand the data, especially the place where there is a cross-system data flows are happening. We are able to stitch those data and try to understand end-to-end data flow. And then the third thing is once we feed in the memory, once we have the granularity and then stitching defined, how we can make sure that those data flows are accurate enough. And as I think we were discussing earlier, the false positives are not free. Every incorrect data flow is waste of the time for an engineer or the team working on that. We kind of tackle this into different layers. So first one is like automated pruning. So for every data flow in the graph, we try to score the flows based on its weightage into the graph. Then we have a human feedback loop where the data which we are showing to the whether human or agent, and if the data is coming back labeled as an incorrect, then we take it back and try to self-improve the graph. And last but not least is a data matching algorithm. This is like how you make sure that your source data and sinks data, those are similar. So we kind of try to match exactly, or we try to identify the transformation and try to see if the data are related between source and sinks. Okay, so let's talk about the challenge too, Aygun.
So actually, I want to shift our focus towards how to generate this graph and then serve it in an efficient manner, right? So this is where actually we observe two competing forces in the same place. So scaling, once we focused on scaling and try to onboard large graphs into memory, so this is where we start seeing some out-of-memory errors or found ourselves accepting some unsustainable infra budgets. And on the traversal side, when we start investigating how traversal happens, actually I can easily say that it's happening in a way of conversational debugging. So first the users or the agents are loading the original version of the swap graph, and they keep asking more questions before they are making an opinionated privacy decision. And we have to answer each of these questions in sub-second time. And this needs to be inclusive of data pruning that needs to happen before we return the response to agent or the human. So over to you, Maharshi, just to see how we achieve this.
Cool, thank you. Yeah, so let's dig into now the performance, right? So far we talk about, right, you have a graph, we fit that into the memory. We have the graph built by the end-to-end, basically this, the systems. But the real question comes is like how we can solve that at the scalable way, right? So the way we try to see this is there is when we see the different type of the storage system, right? There is a fundamental difference between what the traditional, like the disk-heavy storage can provide versus what we can serve in the in-memory, right? So remember, we like kind of build the graph, we kind of compress it. The whole reason behind that was so that we can fit this into the memory. When I say in memory, it is not the traditional disk, it is the cache layer or the server's caching memory. That's where we try to fit that. Before we do into it, right? Before we dig into that, I think the fundamental question is why we need to speed that up, why we need to have to load that into the in-memory. And I think the simple question to that in current world is because of AI agents, right? So they need the sub-second response about the graph. They wanted to understand the graph as quickly as possible so that they can iterate over it and try to understand where are the issues or try to pinpoint it. Same, like I think the developer velocity is also another reason, like the sooner the person who is interacting with the agents or directly consuming the graph, they will see the graph, they will able to understand where are the issues and they can go and try to pinpoint the issues. So for that, I think the one of the core philosophy we took was you take the graph, you load that once into the memory at the start time, and then you serve that continuously, right? And I think as we discussed, we achieve this by you have a compressed size of the graph, which can fit into the memory, and then we let server load that graph into the memory so that you have the complete data into the in-memory. You don't have to go over the network to access the disk IOs. So once we load the memory, right, the next question is how we traverse on that, right? So for traversing, I think we simply use the BFS algorithm, but of course we have a decoding techniques of the compressed graph so that you can basically normalize it and get back into the normal nodes and edge structures. We also applies different, like the rule-based filtering. We also propagate some of the data types. We also have a fan-out detection to understand which node is basically exploding and try to understand the reasoning for that. We try to keep the graph acyclic, so we do cycle detections, as well as we also have the configurable filters so that user can send the specific configurations to access the graph of networks, graph of interest. Now, of course, all the things which we talk about, those are like the development one, but then it doesn't matter if we are not able to operationalize it very well. So we try to utilize some of the standard practice of the operational, so graph rebuilds and updates. So we pre-process the graph or pre-build the graph as much as possible before loading that, so that way we are offloading all the informations away before serving. We have validation methodologies to make sure those graph, the edges and the nodes which graph has, those are basically adhering to the quality bar which we have. Same like we have a serving infrastructure where we deploy those graph and the machines to the multiple layers, and we have the monitoring SLAs where we count the regressions and latencies and things like those. So pretty standard operational principles, but at the scale, each of these items are very important. And I think all those things which we are talking about, the concrete example of that is like how, I think in the morning, our colleagues talk about how the agentic loop can be used. So this infrastructure helps those agents to interactively explore the graph and understand where are the issues, and that can help to fix it. So we have seen those in much in details in the morning.
So by the sake of time, so we will skip visiting all these learnings one by one, but if you ask us to compress all these learnings into one single strategy, we would say, so prioritize quality and freshness, so this will lead into building trust in your graph, and this is the main driver of quick and higher adoption. So this is the end of our talk. Thanks for listening, and we are open for questions.